Okay, so in the last video, we kind of talked about the similarities and differences between quantum mechanics and classical mechanics. And we talked about how in classical mechanics, we kind of want to find x of t, and from there, everything else kind of follows. Whereas in quantum mechanics, we want to find our psi. So, okay, we have our Schrodinger's equation here. And we know that we're going to want to solve this to find psi, and that is something we're going to spend quite a bit of time doing in the future, solving this in this PDE for different environments, different potentials. But it's worth talking about what psi really is, because, okay, we see it's something we're trying to solve, but what exactly is it? Why is it even important? And the reason is that one interpretation of quantum mechanics, which is known as the statistical interpretation, is that if you integrate from A to B, the magnitude of your wave function squared. That's equivalent to the probability of finding the particle between point A and point B at some time t. So that's why it's important, because once we have psi, we can find this probability that we're interested in. So graphically, maybe it looks like between A and B. You can see I kind of shaded this in. You can see at point A here, you kind of have a maximum. At point B, it's a lot less likely that you're going to find the particle there. So that's kind of a graphical way that you can interpret this. Okay? Now, this is pretty interesting because we're dealing with probability, and, it would be nice to say, oh, for sure, the particle is here. However, this interpretation of quantum mechanics introduces probability into the equation. And essentially what it's saying is, even if you have all the information that you could ever possibly want, you can't say for sure where the particle is. So there's different kind of camps and different kind of, I don't know if you want to say philosophies or ways of looking into this. So imagine if you measured a particle and you found it, let's say here. So you're in a lab, you measure the particle, and you find it at this point C. So then what we're wondering is, well, where was C before? So there's a few different interpretations here. The first one is called the realist. And essentially what they're saying is that the particle was always at point C. And the only reason that probability is introduced into it is because what we know about quantum mechanics is not entirely complete. So if we did have a complete theory of quantum mechanics, we could say with 100% certainty that the particle was at C. There was no actual probability. It was just we were kind of missing stuff. So that's one take. Another, which is called the orthodox position, basically also known as the Copenhagen interpretation, is that the particle wasn't really anywhere. The particle was in we'll talk about it more in the future, but a superposition of different states. So it's kind of this position kind of takes the point of view that it's almost silly to ask where the particle was before you measured it. Okay, so this also is kind of weird. Number one, the realist point tells us that quantum mechanics isn't complete, which is pretty interesting. But number two tells us that by measuring a particle, you're almost you're forcing it into whichever state that it's in. So there's something unique about measurement that's not completely understood. And those are two. There's a third one the book mentions, which is agnostic, that it doesn't really matter. They just kind of are solving the problems. Well, long story short, we can say with great certainty that there's not any hidden variables, which is kind of the realist position. That's due to what's known as Bell's experiment, which I think we'll talk about towards the end. But essentially what we get to when we look at this is the active measurement causes the wave function to collapse. So as before, where the wave function might have looked something like this, when a wave function collapses, instead of being all spread out like that, it peaks at wherever it was you measured it at from, or wherever it was you measured it at, in this case, C. Now, these aren't the only interpretations. There's a lot of others, but essentially, for the purposes of the book and the video series, we're taking the orthodox position. And that's the lens we're going to view quantum mechanics through. And going forward, that's how the interpretation we're going to use. Okay? And in the next video, we'll start talking about probability before we really get into the good stuff. And if you like the video, please thumbs up and subscribe. Thank you.